Hi everyone, my name is Geetha. So I am a solutions engineer at Confluent. So today this talk is about disaster recovery for Apache Kafka when it's deployed on Kubernetes. So I'll start off by a brief introduction about myself. So I am a solutions engineer at Confluent, as I mentioned before, and I used to work as a software developer before I joined Confluent. I was a customer engineer at Cloudera and Hortonworks. And then I was a software engineer for several years before that. What I do is I help enterprise customers in their big data journey and identify their streaming use cases and really handhold them and onboard them onto Confluence platform. Act as their thought leader for their architectural design decisions they make, and also influence the sales is what I actually do at Confluent. Please feel free to stop me for any questions if I'm going over the board or really fast. And let's get started. So before I get into Kafka's actual DR scenario, right, I'd like to take back a quick step back and really understand the landscape right here. So in enterprises, there are really two models where before the data infrastructure got really big and huge, there were two problems, or really the two models. One is ETL and data integration space, where organizations had large amounts of data, stored it in data warehouses and databases, and used Hadoop and whatnot for analytics. This approach was great. It had high throughput data transfers, and it worked fine, but it wasn't durable. It wasn't persistent, or it wasn't maintaining the orders, and it had major drawbacks in enterprise setup. So batch wasn't working out. And the other model they had was really this messaging model where it was meant to deliver data in real time. And it took the advantage of low latency, fast, and really high throughput use cases. But this model also had a problem because the data was transient and really real time. There was no way to persist this data. And this is a big problem because of if something goes wrong, there is no capability to replay the history or fix it. And historically, many companies have had huge data influx, and they had to figure out a way, and then entered this new streaming first use case, right? And streaming first enterprise model, where there was this central nervous system introduced at the heart of every company, which made integration simple, understandable, and that helped data become ubiquitous. And that's what started at LinkedIn. Founders of Confluent were originally from LinkedIn. They wrote Kafka. They designed this event streaming platform. The use cases that you see on the left, which is data warehouses that are distributed systems, wanted to move data, monolithics moving on to microservices, batch to real time. This was a platform. The problem really was that these point-to-point connections needed to be decoupled, and the data needs to be easily accessible. So that is what Kafka had really solved. If you see, it's a complete platform. It can move data, transit data, transform data, and also push data to your destination. All of this is with the built-in fault tolerance and reliability guarantees. And Kafka by itself is known to be resilient out of the box with the replication capability and other HA features that are built in, like you can make asynchronous communication, synchronous communication in some areas, things of that sort, using tools like Replicator and Mirror Maker. And now, so Kafka, right? I just like to give a high level overview of people who don't know what Kafka is. So Kafka is this distributed system. It's sort of merging this messaging queue and a file system. It leverages two core APIs. One is producer and consumer clients. Producers write to Kafka and consumers read from it. The nice thing is that these messages are stored in Kafka potentially forever in the exact order they were produced. So there's strict ordering guaranteed, and the persistence, revision, and replay are out of the box with Kafka. The structure that you see at the bottom of the screen is called as topic, which is the unit of abstraction in Kafka. And topic is divided into partitions, and partitions have offsets. So a user, a consumer will always have the ability to replay and go back to a particular offset in time. And because offsets are monotonically in increasing number, the beauty of this Kafka application is that your consuming apps can read from the log from different offsets wherever they want it to be. Now, coming to straight to the point, we are talking about resiliency in Kafka, right? So, what is resiliency anyway? It means having the ability to spring back when disaster strikes, and it is the ability of a server or a network or a storage system or an entire data center to recover quickly and continue operating even when there has been an equipment failure, power outage, or other disruptions. And I found this comic online. I'll give you a second to read it. In case of outage, it is crucial to know what the cost will be to your business while it is in that state. And there will be some threshold the business will not be able to tolerate. So knowing your RPO and RTO will help you decide what you'll need to architecturally keep to keep your business within the limits of the threshold. So Kafka also has its own guarantees and how it enables RPO and RTO. So zero RPO requires synchronous replication in Kafka, which is done with the help of replicator or mirror maker. And zero RTO, meaning which there is no the time recovery time objective, meaning less time before which the clients will fail over or the apps will resume its application logic. Its RTO zero is acquired by seamlessly failing over the clients. And RTO zero means that no manual intervention is required for the failover. Now, before I get into Kafka's actual resiliency model, I'd like to give a quick breeze through of the partitioning model in Kafka. As you can see on the screen, topic is the unit of abstraction. There's one topic X, which has 4 partitions. And there is this concept of leader and follower in Kafka. So the solid blues are leaders and the light ones are the followers. So leaders will have the ability to read and write data, read from the producers and write to the consumers, whereas followers will only be able to read from the producer and they won't have the ability to write to consumer. So clients, when they're connected, they're all connected to leaders. In the event of disaster to happen, the leader will go down and there will be a leader re-election algorithm which will pick one of the followers to become the leader eventually. And then while that is happening, there is an algorithm that runs and keeps this downtime to be minimal and RTO to 0. As you can see, the replicas are placed on each of these brokers, and the replicas are decided by the replication factor. And there's something called as acknowledgements, 0, 1, and all. Acknowledgement 0 means that when producer produces data, it reaches the broker, and then broker sends these data, saves these in the partition replicas, and then the replica, after it is acknowledged that by the broker, it is not acknowledged when it is 0, meaning that delivery of messages is probably not sometimes guaranteed. You may actually lose data if AX is 0. AX all is the best practice configuration most of the production or enterprise grade enterprise customers use in order to ensure there is no data loss or durability of data. Sometimes it may add a little bit of latency, but some people are okay with that. In the consistency availability model, they prefer consistent availability over other parts of the theorem. So this is just on a high level how this thing works. There are situations where some of the brokers will go down. I just explained how it works. When broker 3 and broker 4 goes down, what happens is that the leader on this broker 3 is partition 3, which went down. So it happens so that partition 4. So partition 4, which was originally on broker 4, is now picked as a leader on broker 2. So that's how the shuffling happens, and leaders are picked as and when the disaster strikes. So coming into I'd like to touch briefly upon the certain Kafka constructs before we get into the real, patterns of event-driven resiliency. So the first thing is there is a concept of observers. Observers were introduced on top of native Kafka application. So mostly for intercluster replication between the brokers, it is asynchronous. It's a synchronous fashion. And this is achieved by setting AX equal to all, as I mentioned earlier, and having sufficient replicas positioned across multiple nodes and DCs to meet durability requirements is a must. And in such configurations, producers will wait for all the members to in the ISR, which is in-sync replicas, to acknowledge the receipt of the message. But whereas there are different kinds of Kafka cluster called as multi-regional clusters, where the clusters are spread across many regions. And in MRC architecture, you have a different construct called as observers. These observers will enable you to have asynchronous message transfer. This is done by defining a replica that's already there as an observer as opposed to follower. While followers join the in-sync replica group and are asynchronous with acts equal to all setting, observers do not join the ISR and are asynchronous in fashion. So they bring the benefits like, some of the latency requirements can be relaxed, and you have improved durability because there's no really data loss. Whenever there's a follower going down, you'll always have observer resume the responsibility of ISR. And there's always this automatic client failover benefit in DR setup. So observers can be promoted automatically to become followers. And then that is done by certain strategies, like you can configure it to a certain threshold, like if there are a certain number of under-replicated partitions, observers will be promoted if the ISR drops below a configured count of replicas in the topic replica placement policy. So take a note of this topic replica placement policy. This is very, very crucial when you define clusters on Kubernetes or on-prem or wherever, right? There are really three things that you have to keep in mind, which is rack awareness, replica placement, and observer promotion. These three things are the ones that will keep your data really highly available and make the Kafka cluster very resilient. You can use one of these configurations while setting the observer promotion policy. That way, one of those followers will be promoted to become observer. One of the observers will become a follower or join the ISR list. So that is about observers, followers, and leaders. Now we'll move on to the actual architectural patterns out there that are proven, done and dusted, solidly tested by many enterprise customers. So enter these 4 patterns. One is replicator or mirror maker, which probably is familiar to a lot of you. So there is replicator and mirror maker. They support asynchronous, multi-regional, multi-cloud data replication between one cluster to the other. And there are stretch clusters. I'll go one by one. So replicators, right? They'll allow you to have 2 independent clusters in different data centers and regions. And producers in both the data centers and consumers will be consuming and producing in those data centers. Replicator or mirror maker is a separate application that replicates data from one cluster to another. And active-active is in a setup like that, it requires 2 replicators, and active-passive requires 1 replicator. In this sort of a scenario, you can assure RPO and RTO of near zero, and bidirectional asynchronous replication is possible by this. Replicator is by default asynchronous communication. Moving on to stretch clusters. Stretch clusters are those that have that is really one cluster that is spread across multiple availability zones within the region, and this will ensure you near zero RTO and RPO. Moving on to multi-regional clusters, it's as I said, it's a kind of stretch cluster. It's a different naming convention, but now the clusters are spread across regions, and regions can have multiple availability zones or data centers, if you will. So racks, availability zones are interchangeably used in this scenario. I'm going to use that way. And for native interproper communication, there's synchronous replication, and there's also asynchronous replication supported by observers. And it is very, very crucial to do a good job at defining your replica placement strategy and observer promotion strategy. That way, when disaster strikes and all your followers are going down, your observers will be promoted to join the ISR link, and this can happen automatically. There are also other concepts like follow-up fetching, which is also part of MRC. You can go read up online. This software is really exclusively presented by Confluent, and it's built on top of native Apache Kafka. And cluster linking is another solution in the mix. It also helps with asynchronous replication of data without the use of separate applications. And cluster linking is built on top of replicator. It's a better version of replicator, and it will preserve offsets for you, meaning that you don't need manual intervention is not required when something bad happens, or a region goes down, or a broker goes down. When it comes up, it'll resume from where it stopped off before the disaster happened. So you can take a snapshot of it. This is an overall picture of what is in place right now, what available resiliency options are there for Kafka right now. If you want an RTO 0 based on your company's requirements of more than a 0 RTO is tolerable, then you can go for something like Replicator. If you really want a 0 RTO, then you should consider stretch clusters and RPO, and same applies to RPO and different scenarios that mix and match according to your needs at your company. Like, is it a single, multi-regional, multi-cloud? Based on your requirement, you can pick and choose and mix and match combination of these things. Now, up to the real talk. Why do we need Kafka on Kubernetes? So this is natural, right? Kubernetes is everywhere. Apache Kafka on Kubernetes goes hand in hand with the cloud native development. The next generation of application development is hugely influenced by Kubernetes, and all the cloud native apps are independent, loosely coupled, and distributed services that they deliver high scalability via the cloud. In the same way, event-driven applications built on Kafka are also loosely coupled and are designed to scale across distributed hybrid cloud environments. So it's only natural to think that to marry both of them. And since Kafka consumers rely heavily on persistent storage, and to be able to retrieve this data, Kafka is considered to be a stateful application in the context of Kubernetes. Kubernetes natively exposes abstractions for managing stateful applications, which is called as stateful sets. But Kubernetes has no notion of Kafka-specific constructs by default as such, so we needed it's an additional functionality based on standard Kubernetes APIs to maintain those instances. So in short, Kubernetes has something called as operator, which is think of it as a custom controller, which allows you to expose these applications of specific functionality and automate and scale parts for you. And Kafka fits right in there because Kubernetes has these functionality like config max, secrets, and leverage the self-healing capabilities of Kubernetes with the help of Node and Pod Affinity. If that's really natural that someone wants to do it on Kubernetes. And it along with other benefits like being able to pick the type of storage volume ad hocly and scale it, automate it, however you like it, and also save money by not spinning up resources that you don't want or decommissioning parts that you don't really use on a regular basis is really economical for customers. So they are considering moving on to Kafka, deploying on Kafka on Kubernetes. Now, coming to the differences between deploying Kafka on Kubernetes versus on-prem, disaster recovery is heavily influenced by how networking is set up, how DNS works, and how this whole ecosystem is designed, right? In a normal setup, you would have IP addresses given to you by the provider, and you would work with them. The data centers would know, the brokers would really understand how to talk to each other. But in a Kubernetes environment, you will have to rely on a DNS notation to be able to seamlessly communicate. Then there's this concept of namespaces, and every data center would host a Kubernetes cluster with a distinct namespace, and clusters would be spread across them. And brokers are hosted within the namespaces. There's no real multi-tenancy that you can achieve in a normal on-prem cluster, but in Kubernetes environment you can achieve that. And you can also co-locate your brokers and zookeepers. You can take advantage of Pod Affinity. Really, the Kubernetes operator is the star of the show. It will help you define a lot of things, scale, automate, and allow you to leverage the capabilities of reconciliation, infinite looping, and checking for liveliness and readiness and whatnot, right? And So I just want to reiterate the fact that you should be really, really thoughtful when you design your Kafka workloads. It should be stateful. You should define your config maps ahead of time. That way, because Kafka demands low latency for network, you need to make sure that you have solid state devices for these high performing disks, and consider the location where the data access or broker, is it local or is it where the pod resides? That is where it is done. And it's like because these are all IO intense workloads, Zookeeper and all of these other compute intense ones need high solid state devices. I want to reiterate on that. And configuring Kafka stretch cluster on Kubernetes requires you to define replica placement, rack awareness, and automatic observer promotion. This is a must, and you can do that in the YAML. I'll show you how to do that. This is just a high-level overview of what it takes to deploy Kafka. It's nothing new. It's a custom resource definition CRD, which will help you define different elements like number of Kafka brokers, dependencies, listeners, storage volumes. You can define the space where you're storing all these logs and data. And each of these pod in a stateful set, right? It derives its host name from the name of the stateful set and the ordinal of the pod. We need to create a service for each of these parts in order to enable internal and external access. So we leverage CRDs for that. You can attach a PVC, configure and retain policy, volume type, and CRD. So this is the ideal state, what you would want for a Kafka on Kubernetes setup. So you deploy Kubernetes Kafka on Kubernetes with 3 regions at least, and you have at least two brokers on each in each region, and you have at least one Zookeeper node on all of them in all the 3 regions. And you should set the Zookeeper server ID offset to a different number in each region, and the Kafka cluster ID is the same across all, point to the same Zookeeper. And this is MRC. Remember, it's the same Kafka cluster spread across multiple regions, so you should keep that ID. And you can use kubedns or coredns to expose these regions to the cluster, to the external access. So this is the overall networking setup when you would deploy Kafka on Kubernetes. So resolving networking between Kafka clusters on Kubernetes is very, very crucial to establish seamless connections between pods across Kafka clusters. So the requirement is that multiple K8s clusters will act as a single Kafka cluster. And you need to expose kubedns using a load balancer service, and you need to update the config map with the subdomain to route all the pods from one region to the authoritative server of that region. The IP addresses are now routable, and then you can identify the IP address of the load balancer of the other region, and it will resolve. And now, for example, if you see the East Kafka broker is trying to resolve West broker using the kubedns, and kubedns recognizes the pod in the West region, and then it will get in step 3, it retrieves the IP address and it establishes the connection. So the rule of thumb is that the kubedns in the East cluster is configured for external load balancer IP of the West cluster's kubedns to be the authoritative name server for the West subdomain. And likewise, all pairs of regions you can do this however way and configure it accordingly. The key requirement is that you need non-overlapping CIDR blocks. That way you have seamless connection. You have room for other IP address spaces for different pods that are coming up and down. So there are certain naming conventions for namespace. You want to uniquely name one space per region so that there's no confusion. And then you want to achieve a flat pod networking, meaning that pod IP ranges from a separate cluster must not overlap, as I mentioned earlier. And you also need to allow TCP traffic on standard Zookeeper and Kafka ports, which is 9092 and 8083, between all region clusters and pod subnetworks. So this is where you talk about how you define ordinality in Kafka when there are different brokers, different pods. I'm using pod and broker as interchangeably. So when there are different Kafka pods that are being spun up, as you can see, 0 is the cardinality for the first broker, 1 is Kafka 1 is for the broker 1, and Kafka 2 is for broker 2 in different availability zones. And as you can see, there is this domain name that gets created when you deploy these pods, which is Kafka N, and then the namespace name and the service name dot the region name dot svc dot local. This is how on gkey. This is on gke. So when an external client would recognize the broker using this service. Now, we spoke about defining storage classes and persistent volumes. There are certain settings you need to enable within the YAML file in order to make sure that your volumes are not lost when a broker is down. When you set the volume binding mode to wait for first consumer and the reclaim policy to retain, this will allow the volumes to be reattached to the same pod when any disaster happens. So in multi-regional clusters on presenting. So in multi-regional clusters on K8s, this is how it would look. You have 3 availability zones, and you have the entire AZs are in each region, which we use to establish the rack designations, and a total of 3 racks in each region. So within at least one K8 node in each rack. So we have at least one broker in each AZ and a minimum of 3 zookeepers with at least one zookeeper in each region. So you'll notice that there are 2 observers and 4 replicas that are placed across 3 regions. And topic replica placement will allow you to establish this designation. It is known that setting up zookeeper quorum is critical for setting up stretch clusters in K8s, typically because in K8s, it's crucial to know how many zookeeper pods are there. The naming convention will help with knowing what each of these zookeepers are or Kafka pods are resolving to. Now, when you define a CRD within a YAML, you define it for Kafka and Zookeeper. If you look at what are the different CRDs that are covered within Kafka configuration, you need to define a storage class. That way, you know how much data is being stored. You also have to define rack awareness, that which is covered by the value broker.rack. That way, you're setting replica selector class to rack aware the replica selector, which relies on node labels in GKE and the topology Kubernetes, whichever one you define for your zone. And you also need the version of the broker that the image tag to run in the pod. You have to set the listeners and the domain names, which are external external listeners and inter-broker replication listeners that are very much required. Node pod and node affinity and pod affinity. There is a facility within the Kubernetes to have pod affinity and anti-affinity to co-locate or isolate the resources. For example, you don't want to co-locate like two zookeepers and 3 brokers pods on the same node, right? So you can define which pod goes on which node based on the resource availability that you have. And you want to leverage that in Kafka. There are resource limits. You want to define minimum required capacity for a specific node. You can define that in CRD. And finally, you also have the ability to define zookeeper configurations like dependencies. Brokers can connect to the quorum, and this will help them. Retrieve the metadata. And also, you need to define the number of number of brokers, which is Kafka pods, within the CRD. Now, coming to the zookeeper configuration, the CRD and the YAML, it applies the same with Kafka. You have to define a storage class. You also have to define peer nodes, which will help you define the ensemble to establish quorum. Affinity rules will apply. Replica count for defining number of zookeeper pods. You also have to define log size and data volume configurations, which will help identify the directory where data or logs have to be stored. There are resource and request limits, and every zookeeper will get an ID. You also have to store that, define that in the zookeeper YAML. So when you're testing DR situations in Kafka, there are multiple failure scenarios. One is we have tried this in multiple customer use cases. The first thing we do is we test is when a broker goes down or it was taken down, what happens, right? When a region goes down, what's the path that Kafka would pick in when it's deployed on Kubernetes? When a zookeeper pod goes down, what happens? These are the multiple scenarios you can test for in failure situations. The first thing, when broker pod is gone down, what happens is that there are leaders and followers and observers. So leader was moved from the pod that was taken down to one of the replicas, which are followers. And there are under-replicated partitions, obviously, because one of the leaders is down, and then there are partitions that are waiting to be replicated. And producers were able to produce because there is min in sync replica that was maintained. And observers were promoted to follower ISR replica set to meet the minimum ISR count of 2, and pods came up. And with the self-healing capability of Kubernetes, when the pod comes up, the original pod, which was the leader, was re-elected as a leader replica. And this is it's a beautiful way to test how, it's a really nice way to understand how replica placement works, how observer promotion works, and MRC really plays out. When you induce a region failure, or naturally if a new region is going down, what happened was that leaders got transitioned to another region that has brokers, and automatic observer promotion kicked in. So one of the observers on region 2 got promoted into ISR, which is in-sync replicas, and then producers kept retrying. But there could be slight disruption, but there was no loss of data, at least, because there was always this ISR's observers that were promoted to become replica followers, and then there's this continuous sync of data happening. And minimum in-sync replica was maintained, and there's no disruption to production. So usually what is recommended is to have zookeepers of 5 to be performant and observers to be 3 minimum. You could go with 2 and 3 as well, 2 observers and 3 zookeepers to be highly available. You can pick 3 and a 5 combination. Finally, when zookeeper pods were taken down, what happens was you really, it's like we are all excited about the new PR, the new newly introduced, or it is still happening. It's a new change that's going to come into Zookeeper ecosystem, is that Kafka is no longer going to rely on Zookeeper. It's called as K-Raft. It's a KIP that's coming soon. And the K-Raft it's a KIP 500. If you know the jargon or parlance of Apache software, KIPs are these new requests that are submitted by the community. And Confluent is actively working on removing Zookeeper dependency from Kafka. So that's where you always have to define Zookeeper quorum. You need to make sure that ensemble is always set and maintained. So how do you ensure that things are all good? Because you need to, because you don't want data to be lost, or you don't want systems going down, or service to be disrupted, or business to be having glitches. So some of the best practices that you can make sure you practice before you get into deploying anything on Kubernetes is use event-sizer.io, which is a nice tool that will help you scope and size the Kafka workloads, and it'll actually give you a capacity plan for the Kafka cluster. It'll tell you how many nodes you would need, how much memory you would need on each of those nodes, how much RAM you would need, and all those resource configurations will be displayed to you on event-sizer, and you could map them according to your cloud provider's availability, and then bump the resources as you would need. Use that as a baseline and then build on top of it. You can also explore Confluent for Kubernetes, which is an offering from Confluent, which will help you deploy Kafka clusters seamlessly on Kubernetes, any flavor of your choice. And they rely on, so CFK relies on Helm charts. You could use that. And it's a well-tested product. Many customers are using it. So I recommend you to check that out. And so because Kafka is this really low latency and heavy on network and storage, you want to be very careful on defining your throughputs and avoid any low contention or noise on the access when accessing the storage. So to provide this, you have to use high performance disks, such as solid state SSDs, and consider the location where data access for the brokers is local, or where the pod will increase when overall to support overall system performance. And there are health checks in place in Kubernetes by default, like kube system. You need to have health checks on each of these load balancer services in order to make sure there's no disruption in resolution of names or domains and mapping of IP addresses. And you can define pod affinity rules beforehand. That way, you're not overly allocating or under allocation of resources for these pods. You can use event sizer, and based on that, you can strategize your or placement of these uh, number of pods. And you also have the ability to pick storage class types. There are so many of types that Confluent or Kafka supports. You can pick and choose and type of the volume that you want, and set the reclaim policy to retain. That way, you're not losing the volumes and gets attached to the same pod when the pod comes up after a disaster. And then you always want to automate, use Kubernetes operator in combination with Terraform or some sort of scripting to achieve that. And the general rule of thumb is that you want a minimum of two in-sync replicas and observers, and two observers in each region in order to ensure there's no data loss. But preferably, you want a minimum ISR to be 3. And that's just on a high level, what are some of the best practices that you can achieve. And always monitor, because Kafka is just really developer-centric product that doesn't necessarily have an out-of-the-box UI. So I would say monitoring is a way to handle errors and management of clusters easily. Prometheus can collect metrics from all Java, Kafka, Zookeeper processes with JMX exporter, and it's built in. So CFK, for example, also has a Grafana dashboard for Kafka to visualize key metrics and supplement those metrics with the resource usage and performance. It supports metrics aggregation using JMX and Jalakia, and it supports aggregated metrics and exporting to Prometheus, and you can do all your analytics on top of it. And alerting, triggering, and notifications are all, you can configure them according to your needs and requirements. And that brings me to the end of my talk. Thank you so much for this opportunity, and I hope you enjoyed my talk. Thank you.